So, having explained the nature of simple harmonic motion through rather mathematical terms, let us return to a real life example of simple harmonic motion. The most typical example of simple harmonic motion that is generally described in the physics textbook is a block and spring system. In the block and spring system, a block of mass m is attached to a spring and the mass m is pulled to right for a certain amount. Let us call this amount A. So, an external force is applied to mass m and it is stretched to a point A with an amount of OA, which we call A, and then released. The subsequent motion will be simple harmonic if this distance to which the block is pulled is not very large compared to the spring's length. It is one of the key assumptions in the block mass spring system. Why this assumption? The assumption arises because of two things. The block executes a simple harmonic motion because as soon as you leave the external force, as soon as you stop applying the external force, the restoring force that will arise in the spring is proportional to the amount that you have stretched. In this case, you have stretched an amount A and the restoring force will be an amount Ka. In fact, if you would have stretched by an arbitrary distance x, where x is small compared to the overall length of the spring, the restoring force will be Kx. And the restoring force is such that it tries to bring back this block to the equilibrium position O. And therefore, it is a restoring force, meaning by its nature is to oppose the direction of displacement. It is exactly opposite to the direction of displacement. So, two key assumptions of SHM is now satisfied. One, the force that appears is restoring force and it is proportional to the amount of displacement that you have caused to the body from its equilibrium position. Now, this assumption that the spring should not be extended to a level where the extension or the displacement is large compared to the length of the spring comes from a particular physics theorem known as the Hooke's law, the physics law known as the Hooke's law. Actually, the force is proportional to the displacement of the spring only when the displacement is small compared to the overall length of the spring. This is a direct fallout of Hooke's law, which tells that stress is proportional to the strain in an elastic body when the deformation in the body is small and within what is known as the proportionality limit for that body. This famous law was given by Robert Hooke, who was a scientist of the 17th century. Most of his work was done in the later half of the 17th century. He was a contemporary of Newton, and many historians of science feel that he has not got the right credit that he deserved because he foresaw the laws of gravitation. Though he did not formulate the laws of gravitation, it is he who gave the idea to Newton, many feel. Robert Hooke was not just a physicist, he was a polymath. He worked on microscope, he was a kind of a historian, and he kind of used to observe fleas and insect under a homemade microscope. He has sketched some of the very intricate drawings of insects and fleas, and you can see some of them on the screen as how Hooke's, with the help of his homemade microscope, actually sketched the details of fleas and insects. In fact, he wrote a book called Microphagia in perhaps 1660 or so, and this book contained these neat, absolutely stunning drawings of small fleas and insects, and it is world's first scientific bestseller. In fact, 20 years after that, Newton would write his Principia, something around 1687, and there was a kind of bitter acrimony between Newton and Hooks. Hooks felt that Newton did not give him the credit for his laws of gravitation that he formulated in 1987, and Hooks was the curator of Royal Society of London. When Newton became its president, then he removed all photographs of Hooks from Royal Society. So this is Hooke's law, and it tells stress is proportional to strain when the deformation in an elastic body is within proportional limit, meaning by it is small. So let's return back to the history of science, to the actual simple harmonic motion. Here you see that the body has been stretched. One of the key things that you should remember in this derivation is when you apply an external force Fext, which is symbolized here, this force pulls the mass, and at every step as the displacement increases, you have to match your external force with that extension, otherwise it will not be extended to that level. And ultimately, after pulling it to a level A, at a certain point, you leave the body, meaning by you remove the external force. At that point, simple harmonic motion starts, because the force, let's say Hooke's force, K, immediately starts acting on it, and this force is towards the origin, towards the stable equilibrium position, while the displacement is, as we have measured it, from O to A in the positive x direction. So here is a simplified diagram. This is O and this is x. At any given point of x, remember this was A and the force was acting K. If you would have taken an arbitrary distance x, the restoring force would have been Kx. So this is the diagram. This is at any point x, the free body diagram of the mass. Two things I wanted to tell you. We can describe the body in two different ways, and both of these ways have an impact on the final solution to the displacement that we will derive, as we will later see. The first thing is that we start describing the body at this point O, that is at t is equal to 0, where the displacement was 0. And then we reach a position A, that is the maximum stretch position that we have obtained before leaving the external force. This is at time t, the displacement of the body was from O to A, or simply A. A is also called the amplitude, because when the body will execute simple harmonic motion, the maximum stretch that it will have in the positive x-axis will be A, and then in the negative axis will be minus A, as you will see. Now, as I was telling, that the description of the body will be at t is equal to 0, x was 0, and then it was stretched to A after certain finite time t. This system can also be described from this point onwards, that at t is equal to 0, the body was at a displacement A from the origin, and we start counting time t is equal to 0 from here instead of here. Both will have different connotation, as you will see. So now we feature that the body which was stretched at A starts returning back. So what will happen when it returns back? Under the influence of Kx, the body's velocity will start increasing, but as it increases and it comes closer and closer towards O, the displacement will decrease, so the force experienced by the body will also be lesser and lesser. But the velocity that it has gained, each point of time, the acceleration will contribute to the velocity. So at each point, the velocity will start increasing, though the increase of velocity will be lesser and lesser, because the force itself is getting lesser and lesser. And the velocity will be definitely maximum at O, because at O the force becomes 0. So the body has gained some kinetic energy, it is having a velocity at the point O, and remember, when there is no force acting on the body but there is a velocity, Newton's laws of motion comes into play. The body moves in a straight line, continues to move in a straight line. So as the body comes to O, it has a velocity in this direction and no force acting on it, because the displacement is now 0. That means there is not any extension at the point O when the body reaches this point O in its journey. So when there is no force and there is a velocity, it continues to shoot past O and follow the velocity. But as it shoots past, there is some displacement, and a restoring force kx acts opposite to the velocity, it tries to retard the velocity. Depending on what velocity, what maximum velocity it gather at O, it will shoot past to a point B where its velocity will be 0 under the retarding force. Again, the force that is incidental on the body at point B is maximum kx, but it is in the opposite direction, that is the restoring force, and so it will start accelerating towards O, back again at O, again maximum velocity with 0 force, again shoots past O towards the right, and the body will execute simple harmonic motion from A to O to B, then B to O to A. The total time taken for the oscillation is called the time period of the block of the mass m. That is the time taken for the body to start from A and reach at A back. That means A to O to B and then B to O to A. Or in other words, in the other system, from 0 to A or the O to A, then A to O, then O to B and B to O. If we are describing, since we are describing at x is equal to 0, t is equal to 0, then the actual motion will be from O, it will go to this and then return back to O and then shoot past to B, then B to O, back again. So how do we describe the motion of this body? To do that, we have to draw a free body diagram of the body at a distance x from the origin, and let us take at a distance x from O in the positive x-axis. As in this diagram, at this point the displacement is x but the force is kx to the opposite direction. So what is the laws of motion tells you? The Newton's laws of motion tells that the net force acting on the body is equal to the acceleration times the mass. So net force is equal to mass into acceleration. So what is the net force acting on this body at this point? It is kx, but it is in the opposite direction. So net force is equal to minus kx. This is equal to m into a. We all know that acceleration is rate of change of velocity, which in turn is rate of change of displacement. So a is equal to dv by dt, or is equal to d by dt of dx by dt, where x is the displacement. This is equal to d square x by dt square. This is a very well known identity. The acceleration of the body is double derivative of displacement. It is d square x by dt square. So our equation boils down to m d square x by dt square is equal to minus kx, or m d square x by dt square plus kx is equal to 0. This is the equation that we got. M d square x by dt square plus kx is equal to 0. M d square x by dt square plus kx is equal to 0. This is also written as d square x by dt square plus k by m x is equal to 0, where k is called the spring constant. Yes, in the case of elastic body, I told you that k is a proportionality constant. In the case of spring, k is called the spring constant, where k is equal to spring constant, m is equal to mass of the block. Mass of the block. Now, you see, this is a different problem than the translational motion. In a translational motion, the acceleration was constant. You were asked to find out displacement given certain variables, or you were asked to find out velocity given certain variables. But here, the acceleration is changing with respect to the displacement. The acceleration itself is increasing or decreasing depending on where the body is. And that is why we get this equation that the double derivative of x with respect to time plus k by mx is equal to 0. Now the question is, what will be the displacement of the body at a time t? That is the answer. That is the question, and we will find the answer. What is the description of motion? That is the displacement, the acceleration and the velocity at time t. The total simple harmonic motion solution is to find out that if you disturb the body from equilibrium when it is attached to a spring of spring constant k, what will be the periodic motion's time interval? That is, after what time period will it return back? The time period of motion, and given the time period of motion, what will be the velocity, acceleration and displacement at various point of time? That will give us the complete description of SHM in case of a block spring system, and that depends on how do we find the solution to this equation d square x by dt square plus k by mx is equal to 0. A little bit of mathematics is involved here, and in the next we'll go to this, how to solve this equation in two different methods. One mathematical way, and the other one is a very intuitive way by relating the simple harmonics motion to uniform circular motion. Because uniform circular motion itself, when seen from the side, or when you point a light at a uniform circular, a body executing uniform circular motion from the sideways, you will find that the shadows of the body actually move up and down in a simple harmonic motion. The similarity between uniform circular motion and that of simple harmonic motion as in a spring block system gives us a very elegant way of solving for displacement, acceleration, time period and virtually anything that we want to know about the SHM.